So what we'll do here in this virtual lecture is we're going to use our knowledge of group theory and use that to predict some vibrational spectra, either infrared or Raman spectra, of molecules that have ligands that stretch or bend or wag or whatever they do under those conditions of irradiation. Okay, so what you can actually do are two different things. The first one is a stretch-only analysis, where you just look at the stretching of the bonds. And a lot of times this is enough to tell you the information you want to know about the molecule. The second thing we could do is a total vibrational analysis, which is a little bit more complicated, but gives you more information about other deformations and stuff that are in there that aren't just stretches. So why would one want to do this? Well, let's say you took platinum dichloride and added to it phenyl isonitrile. You would get one of these two complexes. Probably both, as a matter of fact. But let's say the reaction conditions were such that you just got one, and you wanted to know which one you had. It turns out, with group theory knowledge and how to use it, you can take the spectrum and immediately ascertain which is which. And so that's the focus of what we're going to do here with this. And so we have two possible isomers that can occur. This one is the cis one, where both isonitriles are on the same side, or this one here, the trans, where they're opposite each other. Now, as it turns out, right, these are both, we would say, in terms of Vesper theory, square planar. Okay? But they do not belong to the same point group because of the difference in the disposition of the ligands. In fact, neither of these are classic square planar point group D4H. Right. Tetrachloroplatinate, PTCl42-, which we did in class, is, but these aren't. And so the first thing we've got to be able to do is to find the point group of these molecules. And so how do we do that? The usual way. Let's start with this one. What's our axis of rotation? Now, if it were actually D4H, right, that's where you have the C4 axis coming in and out of the board. This isn't that. Instead, what we have is a C2 axis in the plane of the board. So vertical, again, is going to be in the plane of the board here. All right, so that's the first criterion on our flow sheet. On our flow chart. Do we have a principal axis of rotation? Yes, we do. The symmetry is C2, though, not C4, as it would be if we had 4 chlorines or 4 isonitriles or 4 whatever around the center. All right. The next question is, are there then 2 perpendicular C2 axes? I challenge you to find that in here. And the reason I challenge you to do it is because it's not there. Okay. We don't have that condition met. So this is a C symmetry molecule, not a D symmetry molecule. And the next question is there a horizontal plane of symmetry? That would be like so, coming in and out of the board, but at a 90-degree angle to our C2 axis. Obviously, that's not there, because if you reflect this over to here, through that plane that would be here, you have a chlorine switching position with an isonitrile. That doesn't work. But we do actually have a plane of symmetry in the board, again, which contains that principal axis of rotation. Therefore, that's a sigma b. Okay, and then there's one coming in and out of the board, containing, again, that C2 axis. That's another sigma b. And if you take all that into consideration, the cis isomer is, there it is, C2v. Okay. Now what about this one? Well, in this case, we actually do have a rotational axis coming in and out of the board at the central platinum. And if you look at that, right, it's not a C4 axis, but it's a C2. If I rotate this by 180 degrees, these chlorines swap places and these isonitriles do too. And so that is a C2 axis. And again, that's vertical. That's the Z axis. that's coming in and out of the board at you, are there two perpendicular C2 axes in this one? In this case, the answer is yes. There's one here. And there's one here. Now recall, we're regarding these ligands as spheres, which is kind of a stretch for a linear thing, but those actually do line up in a straight line all the way across. The phenyl, the carbon, the nitrogen, the platinum, the nitrogen, the carbon, the phenyl. So, yes, we have two perpendicular C2 axes. So this is D symmetry, not C symmetry. And then the next question is, do we have a horizontal mirror plane? Again, because your vertical axis is coming in and out of the board, we actually do in the plane of the board have a plane of symmetry, but that plane is in the plane of the board, perpendicular to the principal axis of rotation. That's a sigma h. And so therefore, the axis that we have here is, or the plane we have here is sigma h. The symmetry is D to H. So two different symmetries on this. So now what we're going to do is the vibrational analysis itself. So let me get the molecule redrawn for our reference. We'll put it over here. And we'll consider the two of these in turn. So let's look at the cis isomer. It's C2V. Our character table has the identity, a C2 axis, a sigma XC, and a sigma YZ. Again, that's right off the character table. And again, the character tables will be provided for you on the exam. The thing that won't be is that flow chart that got us to determining what the point group is. So I'm going to take the textbook here and get the appropriate character table available. Now remember, the next thing that we got to do is we have to define our Cartesian coordinate system. And so we don't really have a choice in the matter, in that the fact that this, in the plane of the board, is going to be the z-axis, right? Because that's where our principal axis of rotation is disposed. The other two are up to you. And so we have to have x and y symmetry somewhere. I'm going to do it this way, where I put this axis also in the plane of the board. And I'm going to call that y. And then coming in and out of the board at us is x. Now that's important for defining our two planes of symmetry. Right? So we got to do that. Again, you can do it however you want. But once you do it, you have to be consistent throughout the rest of the exercise that we're about to go through here. So let's do stretch analysis. Stretching only. So what we're going to look at is what happens when these triple bonds here deform as they're irradiated with infrared, or Raman, which is effectively the same thing, energy. And so the first thing we're going to do is we're going to generate what's called gamma stretch. This is nothing more than a reducible representation that we can make, considering the number of unmoved, in this case, vectors. And so again, these bonds are going to stretch, and we have to see which operations keep the vectors where they are, point in the same direction that they are, or which ones move them. Now it turns out, again, we don't have to do vector sums and all that kind of business, luckily, for this. All you have to do is focus on the number of unmoved, in this case, groups, or atoms. Count this as one thing and that as the other thing. If it stays put, it's going to have a character of 2. If they move, it's going to have a character of 1 or 0 or whatever happens. So let's first then take our identity. If we do nothing to that molecule at all, do either of the isocyanate groups move? No, they don't. And so the character for that is 2. If I rotate about my principal axis, which again is here, then the top one exchanges for the bottom one, and the bottom one exchanges for the top one. So if we want to call these 1 and 2, which you can also do, right, those are going to interchange. And because of that, the character for that symmetry operation is 0. Next, our planes, sigma xz. Now this would depend on what your coordinate system was defined as. If you're going to go with the one that I have here, the xz plane is actually this one. All right, so along that axis right there is also the sigma xz plane. And so if I reflect about that, again, 1 swaps with 2 and 2 swaps with 1. Right? The x-axis is coming out, so the xz plane is parallel like here. That swaps those two. The character for that is 0. However, the yz plane is the plane of the board. And so the yz plane contains, see that? Yes, okay. Contains both of those groups. Therefore, they don't change position. They stay where they are. And the character for that is 2. So now what we're going to do is we're going to reduce our reducible representation. And this is like what we saw in class last week, where you test the irreducible representations in the character table against this and see which ones contribute. All right, so let's do that for all of them in turn. For the totally symmetric representation, the order of the group is 4. We have 1, 2, 3, 4 classes of symmetry elements, all of which contain only one element. And so we're going to take 1 over h, or 1 over 4, times the number of elements in the class, times the coefficient for our reducible, times the coefficient for our irreducible. Let me move that down just a second, so we can keep track with what these are. A1 is the totally symmetric representation, where everything is a 1, a positive 1 that is. And so, since all of these are 1s in front of here, I'm not going to go ahead and write those down, but we have 2 times 1 plus 0 plus 0 plus 2 times 1. And that means that the contribution of the totally symmetric irreducible representation does appear. If we now then consider the next one down, which is on the character table A2, you can probably already see what's going to happen there. We have 2 times 1 plus 0 plus 0 plus 2 times minus 1, which gives us 0. So there is no contribution from the A2 irreducible representation there. So gamma stretch so far is A1. And because the character here is 2, we have to have, there's got to be one more of them that actually participates, because we only got, from the totally symmetric representation, one of the two things we need. Next up, B1. And the characters for that are 1 minus 1, 1 minus 1. Again, I'm reading that directly off the character table. And so A for B1, again, is 1/4, 1/4. 2 times 1 plus 0 plus 0 plus 2 times -1 or 0. So no contribution from that either. The last one, B2. We have 1/4. 2 times 1, 0, 0, 2 times 1. So, our gamma stretch is composed of A1 plus B2. And so we've reduced that. And so with something with this type of symmetry, this is a fairly quick exercise, as you can see. So let's rewrite that here. Gamma stretch is equal to A1 plus B2. And so you can probably see from this, right, these are the two that are contributing. What I say here holds true here. If I add 1 plus 1, I get 2. 1 minus 1 is 0, 1 minus 1 is 0, and 1 is 2. And so that does work for both internal checks there. Now, if you had actually taken the y-axis as coming out of the board and the x-axis is in the board, then you'd actually have A1 plus B1, but you would find that it would also, you'd have a 2 here and a 0 there, and it would still work that way. All right, so once we have that done, how do we determine the activity of these? Are these stretches, which have these symmetries, active in the IR or the Raman? And the way that you do that is you go over to the two columns that lie beyond all of our characters. Now, these aren't defined as anything in the book, but what we used to like to call these is set 1, the first one, and set 2. And in there, you'll find something, or you'll find nothing. Now, in C2B, there's actually something on each row for everything. So if I just go ahead and reproduce the character table up here so you can see this, since it's the first time we've done it. And this is just a reproduction of that character table. What did we see in set 1? So you look over there, and you see, let's copy this right now, A1, there's a Z in there. A2, there's an RZ. B1, there's an X and an RY. And B2, there's a Y and an RX. So what does this mean? Well, for our purposes, don't worry about these, because you can also use this for rotational spectroscopy, microwave spectroscopy, to determine if things are going to be active in that realm of the electromagnetic spectrum. if you see an X, a Y, or a Z in the row with your irreducible representation in set 1, what that means is that that symmetry is IR active. If there's nothing in there, or if there's just an R, then it's not. And so, to say that again, A1, B1, and B2 are IR active. A2 isn't. And so, on these, which one is IR active and which one's not? Well, it turns out they both are IR active. And then more on how you interpret that in a second. If I put into set 2, what we see, we have x squared, y squared, comma z squared, xy, xz, yz. Set 2 tells you whether an irreducible representation or a vibration with certain symmetry, which is what we determine here, is that Raman active. If you see anything in there, in this column, set 2, then it is Raman active. Don't worry about what that notation means. That actually means that the x squared minus y squared d orbital and the bz squared orbital belong to that set 2. We'll look at that when we put this in the context of bonding. And of course, these are the symmetries of the other 3d orbitals. But for vibrational spectroscopy, if you see anything at all in the column across from your irreducible representations, those are Raman active. And so, both of our symmetries are Raman active too. So to boil down what you would actually see based on this is each symmetry that you see, if it's IR or Raman active, gives you one band in the IR spectrum. So there are 2 bands in the IR. So you see two peaks in the IR spectrum, somewhere between 1,500 and 1,900 wave numbers, or inverse centimeters, which is the proper term for that unit. In the Raman spectrum, again, you would also see 2 bands. And we'll get into what happens if you have a degenerate one and that kind of stuff after we get done here with this. So, we've just determined that the cis, C2V, would have 2 IR bands and 2 Raman bands. All that work just to tell us that. But again, once you do this, right, if you had another molecule that was a cyanide molecule, a carbonyl molecule that was cis with 2 fluorines, and that type of molecule like that, a flat one, a planar one, same. And so once you get used to this kind of stuff, you can look at the molecule and say, okay, that spectrum corresponds to this. So that's the ultimate point of doing some of this kind of stuff. What about our other one? Let me get to the proper page here in the textbook. So you'll find this D2H on page 663. This has a lot more symmetry elements in it, as you might expect. And so let's draw the molecule. Because again, you're going to need to put the coordinates in. Okay. And we got to do the same thing across the board. And so, once again, our rotational axis, make sure this will fit here, one coming in and out of the board, the principal axis, the C2 axis, has to be vertical. We can define our coordinate system like this. In fact, why don't I just draw it right on the molecule itself? Where here, at the center, is the z-axis, and I'll call this one the y-axis, and that one the x-axis. And you can do it in reverse if you like, just making sure that the z-axis is the vertical one. Let's then generate a gamma stretch for this molecule. So you have E, as usual, C2Z, C2, I think it's Y that comes next, right? Yep, Y. C2X. The inversion center, since we have one of those, sigma XY, sigma XZ, and sigma YZ. So what happens with this, what you end up putting down here, especially over on that end, in these two axes, will determine how you picked your Cartesian coordinate system. Again, it's up to you which axis you labeled X and Y. As long as you're consistent, you will get the same result. Let's generate a gamma stretch for this one, and then we're going to reduce that. So, for the identity, how many isonitrile groups remain in place as before? 2. For the C2 axis, that's Z, that's the principal axis, who's coming in and out of the board. If I rotate that 180 degrees, isocyanide 1 and isocyanide 2 switch places. And so that's a big 0 for that one. If I rotate about the y-axis, again, 2 and 1 change place. 0 there. However, since the x-axis contains both of these groups, rotating about it leaves them where they were. That's a 2. And as I've alluded to in class before too, right, the inversion center swaps everybody everywhere, and so as a result, those will also change places, and that's a 0. The xy plane, which is the plane of the board, those don't go anywhere. The XZ plane, which is coming out of the board at you at a 45-degree angle, is this plane right here. That contains those two ligands. And so as a result, they don't move. But the YZ plane, which is at a 90-degree sense to that, does swap them once again. And that's a 0 for that. So again, the gamma stretch is a gamma reducible, and we can reduce that based on the symmetry of the group. And so, which one, or what do we do first? We need the order of the group. It's 1, 2, 3, 4, 5, 6, 7, 8. We have 8 symmetry elements in here. Not 4. But that's no problem. Now again, one of the tricks you can do with this is wherever you have zeros in your stretch, or gamma stretch, or gamma reducible, or whatever you're doing, you're going to get a product of 0 out of that. Right? You multiply by 0. So you can ignore essentially those symmetry elements, which saves you room on your paper when you're writing this stuff down. Again, each class of symmetry element has only one member. And so the coefficients in front of here are 1. And so it's kind of redundant to write that down as well. So let's get to the reduction part. Let's see what the contribution of the totally symmetric AG contribution is. And so AG has 1s. Once again, I wrote that too close. All the way across the board here. And so we're going to get 1 times 2 times 1, or 2. 0, 0. 1 times 2 times 1, or 2. Another 0. A 2 for here. A 2 for there. And a 0 for the other one. And so the contribution for A Garada is 1. The next representation down is B1G. And there we have this 1, 1, minus 1, minus 1, 1, 1, minus 1, minus 1. Let's look at the contribution for B1G. 1 times 2 times 1 is 2. 1 times 2 times minus 1 is minus 2. 1 times 2 times 1 is 2. 1 times 2 times minus 1 is minus 2. So that's a 0. No contribution for B1G in here. So I can keep tally over here. The 1 isn't necessary for that. A1G, or AG, so far as what we have. Next, irreducible down is B2G. And here, we have 1, minus 1, 1, minus 1. 1 minus 1, 1 minus 1, like so. And so what's the contribution of B2G? That's 1/8. 1 times 2 times 1 is 2. 1 times 2 minus 1 is minus 2. 1, 2, minus 1, minus 2, and 2. So 0 for that one as well. Now, also keep in mind, in the same context as what I said about the reducible representations, if something happened where you got a number that wasn't divisible by 8, something's wrong. You messed up one of your symmetries, you messed up one of your Cartesian coordinates, and if that happens, then you need to go back and see what's wrong. But that's what's kind of neat about this stuff, is there's an internal check that once you hit the barrier, you're like, well, I gotta go back and fix it, and then you can. Okay, so that one doesn't contribute. Next up, B3G. And the characters for this are 1, minus 1, minus 1, 1. 1, minus 1, minus 1, 1. So, how about this one? We have 1/8. 1 times 2 times 1, 2. 1 times 2 times 1, 2. Minus 2, minus 2. 0 doesn't appear. So far, we're striking out. Okay? But because the totally symmetric one, the first one, contributed, and that's usually going to be the case too. There's only one more of the other 7 that are left that's going to contribute. So chances are when we find it, it'll be the right one. How about AU? That's the one where we have all the negative ones on the one side. Notice that is a -1 with respect to the inversion center, which is a definition of ungerade, uneven. And so if we look at our contribution here, again, it's going to be 2 plus 2 minus 2 minus 2, 0. So no contribution from that one either. Next is B1U. So we've got 3 more to go. Hopefully one of them will register, and that'll be our correct one. That's like this. Contribution is 2 minus 2 minus 2 plus 2. So no on that one either. B2U. That's that one. We have 2 minus 2 plus 2 minus 2, 0. So we have one more. We hope this fits, because if it didn't, right, so if we get a 0 here, we did something wrong along the route that we took. And this one is like so. Okay, so let's hope we get a 1. And you can probably tell by inspection right there, we're gonna, because we have 2, 0, 0, plus 2, 0, plus 2, plus 2, and 0, 1. And so the 2 symmetries that we have are AG and B3U. If your Cartesian coordinate system was different, meaning you put the x-axis where the y-axis is, you'd get a different answer to this, but the ultimate outcome will be the same. Okay, so again, when you get used to this, or if you're comfortable with it, you can tell which ones are going to work and which ones aren't just by when you write these things down, comparing them. But let's translate that over to here. Are these IR and or Raman active, and how do you know? You go over to set 1. So for the totally symmetric representation here in the column in set 1, what do I see? Nothing. It's blank. And so this symmetry is not IR active in this molecule. In set 2, however, what I see is x squared comma y squared comma z squared. Whoops, not there. So there's nothing in here, but there is something in set 2, and so this is Raman active. What about the other symmetry that came out of our reduction? In set 1, I see an x, not an r sub x, a regular x. So again, that was Raman active. Here, we have IR active because there's something in set 1 for B3U. There is, however, nothing in the Raman. It's blank. There's nothing in set 2 for B3U. And so after all of that, then here's our conclusion. The cis isomer, which is C2V, has 2 IR and 2 Raman bands. Trans isomer, which is D2H, has 1 IR and 1 Raman band. So, by either type of spectroscopy, you could tell these two apart. In the infrared, you'd see 2 stretching frequencies in their infrared. You would also see 2 stretching frequencies in the Raman. In the trans one, you'd see 1 band in the IR and 1 in the Raman, and therefore, if you had only one of the two, this would tell you what it was. Just an aside, and we'll probably get to this at some other point during the class, but this does show up on things like graduate student qualifying exams and things like that. If you step out there and say, oh, I took the infrared of this, or I took the Raman spectrum of this, somebody might say, well, what are you measuring by those types of spectroscopy? Now, they're complementary to one another, but answer that question. Infrared measures a change in the dipole of the molecule. Okay, so if that's what that does, what does Raman measure? Measures a change in something too, right? In any type of spectroscopy, you excite a molecule, it relaxes, and then you see what's going on, or maybe you're measuring the excitation. In Raman, you see a change in something too. It's a change in polarization. So effectively, you perturb the electron cloud around whatever you're looking at. That's why that has a 2-dimensional component in set 2, and this has a 1-dimensional component in set 1. And so that's just sort of an FYI thing. But you'll need to do this type of vibrational stretch-only type of thing. And so we'll stop there for now, and in the next video that'll be up here, Vibrational Analysis 2 will show us how to do a full stretch analysis on a molecule.